First of all a scatterplot is graphing ordered pairs. Early on, I asked people if they understood what a dot plot was, and many people confused dot plots early on with scatter plots. So in AP statistics, a scatter plot is a graphing of ordered pairs. Okay, so things like height versus weight, age versus the number of children, that sort of thing. Okay, you can do price of pizza versus number of toppings, as long as it's numerical versus numerical, and every point represents an individual. Okay, it must be quantitative. And we can't graph categorical variables in the same way. So you couldn't do something like age versus gender. Okay, it really wouldn't make any sense. We could do something where we color code. I mean, that's always possible, but we don't really worry about that. So we need to get some new vocabulary. Okay, in the past, in every other class you've ever been in, when we talk about scatter plots, we think of the independent variable on the x-axis and the dependent variable on the y-axis. In this class, we don't do that. Okay, typically we could choose anything for x. Okay, and the y variable is the dependent variable, and y would depend on our choice of x. That was the whole point of independent versus dependent variables. Okay, makes a lot of sense. But there's a problem with when we talk about AP statistics. We have other words. Pardon me. There are other definitions for the word dependent and independent that we want to use later on. So instead of using the words independent and dependent to talk about scatter plots, we use the term explanatory variable for x, and for y we call it the response. They're really very similar in terms of their meaning, right? The response responds to the explanatory variable. Okay, the explanatory variable can be explained by the y. Okay, so explanatory is now the x variable and response is now the y. So I will never ask you about independent versus dependent in this context. Instead, I'll ask you about explanatory versus response. Okay. Again, we already have these notions of independent and dependent variables. Okay, and we haven't talked about contingency tables. That's okay. So, how do we decide which variable is which? Okay, so here's the idea. Dosage of a given anabolic steroid versus the number of home runs hit. Okay, so in general, if I were to tell you, okay, Barry Bonds had this much steroid versus this many home runs, and Sammy Sosa had, it's a silly example, but if I gave you the dosage versus the number of home runs just as a data point, okay, how would you decide which one was the explanatory and which was the response? Okay. To me, I think the amount of steroids explains the number of home runs. So I would tend to put steroids on the x-axis and number of home runs on the y-axis in that case. It just depends on your point of view, really. How about the number of cavities versus the number of visits to the dentist over the last 3 years? In general, okay, do you think the number of cavities explains the number of dentist visits, or do you think the number of dentist visits explains the number of cavities? You can look at it either way. I tend to think here that the x variable, the explanatory variable, should be the number of cavities. Okay. How about height versus weight? This is a little trickier, right? Does weight explain height, or does height explain weight? Now, depending on your context, it might be really, really different. For babies, for instance, height doesn't really do much for you. Weight is a much more interesting variable that might help explain the size of the baby. As you get a little bit older, right, people's weight fluctuates more, so perhaps height explains weight. I don't know, okay? So it's going to, in a case like this, it might depend on your context. Are you trying to create some relationship where you try to explain someone's height based on their weight, or are you trying to explain somebody's weight based on their height? Okay, it's going to depend on your context sometimes as to which one is the x and which one is the y. Okay, so graphing a scatter plot, really not that tough. I'm not going to go through it in depth right now. We'll do some examples in class where you get to do it hands-on. This is some data from college football season several years ago when Hawaii was racking up crazy passing yards. But if we look at this, we can look at some various different things. I'd be interested in the number of points per game. That's the second column after we're at 51.9, 46.2, versus the number of yards per game. And I might try to decide, well, which one makes the most sense as an explanatory variable versus a response variable? Do you think the number of points should be the explanatory variable and explain the number of yards? Okay, or do you think the number of yards might help explain the point total? I tend to think it's the second. So I think that even though we're looking at yards on the right, the 532.8, okay, I think that probably should be the x variable, okay, because it's probably more likely the number of yards is going to influence your score, right, rather than your score influence the number of yards you get. Okay, so what is it we're going to do in class next time? And that is put your explanatory variable into list 1, your response into list 2, and the first option in our stat plot screen is going to be our scatter plot. We're going to zoom stat, and we're done. Okay? So that's it. Okay, that's what graphing scatter plots is about. That should be pretty straightforward. We've been doing graphing scatter plots since like the 3rd grade. Here's some observations, okay, that we're going to try to make. So what kind of observations can we make about the graph of the data? Okay, so first of all, positive association. What does that mean? As the explanatory variable increases, so does the response variable. Okay, which would mean that negative association says that explanatory variable increases, the response variable decreases. So as one increases, the other decreases. So positive association basically means that we're going up, and negative means we're going down as we read left to right. Okay, and we can ask ourselves, is the trend positive or negative? And we think about in football, as you increase the number of yards, do you expect your score to increase or decrease? You expect your score to increase as you gain more yards. So we expect that to be a positive association. In general, the slope of the line is going to be positive if it is a line. Okay, so let's get some things about correlation cleared up. First of all, the last thing I talked about said association. I didn't use the word correlation. I did not use the word correlation intentionally. So what is correlation? It's the measure of the linear relationship of data. This is super important. And if there's nothing else you get out of this section, it's that correlation is the measure of the linear relationship. Okay? It only measures how linear it is. We could have a squiggly line. It could be in a perfect squiggly line. If it's not linear, the correlation is poor. Okay? So the correlation coefficient is R. And I've got some facts here coming along the screen. So first of all, the facts about R varies between -1 and +1. Okay? If R is positive, it means we have a positive association or correlation. Okay? That means the trend is going up. If R is negative, that means the correlation or the association is negative. It's going down. When R is close to -1, we have near perfect negative association. So it's almost a perfect straight line if it's near -1, but it's going down. And if it's near +1, it's almost a perfect straight line, but it's going up. When R is close to 0 on either side, the correlation is weak. When we talk about R, that's all we can say. Strong, strong, weak. Okay? And we can tell you which direction in general the data is moving. And remember, again, strong linear fit. Okay? It doesn't tell you anything about the curve, if there's some kind of weird curve in there. Okay, so here's a graph of some data, and this is points per game versus yards per game. Hey, how about that? And you can see in this case, I've chosen to make my x variable the points and my y variable the yards. Now, if I were to do this again, I'd probably switch those because I think that's probably more yards per game probably explains points per game better. Okay, that's my correlation, my graph. Okay. So the question is, now how do we come up with R? Let's go back to that picture again. Oh. Okay, let's go to this picture and try to decide R has got to be positive here. Okay, it looks fairly linear, not terribly grouped, but fairly linear. So R is going to be somewhat close to the number 1. Okay, because it's a positive number and it's strong. Had this been a decreasing trend, we would have said, okay, well it's somewhat strong, okay, but the correlation is negative, so we would make that number. The R in that case would be closer to a -1. Okay, so how do we find R? How do we calculate it? All right, I'm going to walk you through this. This is not something you have to be able to do on a daily basis, but you need to know where it comes from. So the x and the y's both have means and standard deviations. Okay, so each point can also be reduced to a point that's basically z-score, z-score. Right? Z-score of the x value, z-score of the y value. Okay. We can get a sense of the total z-score for a point by taking the product of the two, right? So if the z-score for x is -1 and the z-score for y is +2, I can combine those two and multiply them together and get a sense of the total z-score for that point by taking the product of the z-score of the x value and the z-score of the y value. Okay, now to get r, all we do is we sum up each of those completely and divide by n minus 1. Okay, and again, that n minus 1 crops up again, just like it did with standard deviation. Okay? All right. And again, before we get into regression, we're going to get there. Well, before we get to regression, I just want to point out that we're going to learn how to do that on the calculator as well. This is not something you're going to have to do on your own with the calculator very often. You're not going to have to do those z-scores and multiply the z-scores and divide by n minus 1. There's a shortcut for r in the same way there's a shortcut for mean and standard deviation and all that stuff. So you don't have to have that memorized. It's okay. Okay? But what we have now is this measure r that gives you a sense of how linear are the data. Okay? But the next thing, of course, is going to be regression. Okay? And linear regression is what we're doing, and this is what we think of as a line of best fit. You're not going to hear me use the term line of best fit very often. Instead, you're going to hear me use the term regression much more often. Okay, so the question is, what would a line of best fit look like? Okay, we have to define a few things. The first term is residuals. This is an absolutely important vocab term. The residual is the difference between the predicted value by the regression line and the actual value. Okay, so if we think of a regression line is going through some data, okay, a line of best fit, for every value on the regression line, we can find a distance from that value on the regression line to the point above or below it that's in the data. Okay, and the idea here of regression is that if we have a line of best fit for the data, then ideally the best regression line is the regression line that makes all those values as small as possible. All those little residuals very, very small. Okay, here's our picture again. Okay, again, now I have pass yards versus points per game. Okay, so if I run a line of best fit through this data, the distance from each point to the line should be collectively very small. So I define the residual as the actual value of the point minus the value of the point on the residual line, on the regression line. Okay. The predicted value for x on the trend line is y. We call it y hat. Kind of funny, I know. Okay. And the actual point is y. Okay. So I'm taking the difference between the point on the line and my point in the data. Okay. And again, as I said, these differences should be as small as possible. And we always keep them that way, where it's going to be datum first, regression second. So that means that a positive residual tells you we're above the line, and a negative residual tells you we're below. Okay. Again, just as with standard deviation, okay, to talk about the collective total, we don't want to add the positives and the negatives together. Instead, we square them to make them all positive. Okay. And so what we do is we take the sum of these, and the regression line that we're going to use is called the least squares regression line. It's where I take all the residuals, okay, I square them and make them all positive. The regression line we're interested in is the one that makes that sum total of the squares of all the residuals as small as possible. It's the least of the squares of the residuals regression line. Okay. Okay. So to find the least squares regression line, this is what we would do. Again, this is not something you're going to have to do in practice. Okay. We would look at the graph of all the z's, okay, the standardized points that we saw first. Okay. And first of all, notice that the mean point is 0, 0. So it's reasonable to expect that the line will go through that point. Okay. So our regression line should be of the form z sub y hat is equal to m times z sub x. Okay. And what's cool about it is that to get from a z-score in x to a z-score in y, the slope that we use is r. Just works out nicely. Okay. So moving one standard deviation in x moves r standard deviations in y. Okay. Let's say that again. Moving one standard deviation to the right in x will move r standard deviations in y, up or down, depending on if r is positive or negative. So that's the relationship. Okay. That r is a relationship between the standard deviations of the x variable and the y variable. Okay, So how about with real data? Okay, that is data without a z-score handy. Okay, so basically, we use the model y equals mx plus b, but in statistics we always use the form y equals a plus bx. Okay, and the answer is because it's kind of a tradition thing. Okay, so in our class, b is not the y-intercept. In statistics, b is the slope. Okay, I know I teach Algebra 2. It gets confusing for me sometimes too, but you'll get used to it. Okay, so the slope r moves the line 1 standard deviation in the x direction for every r standard deviations in the y direction. Okay, that's what we're talking about. So we're going to try to use that to talk about how to find the new slope. So the way we find the slope is we take the regression, the correlation coefficient r, and we multiply it by the standard deviation size of y divided by the standard deviation size of x. Okay. Okay. So basically, what this does is the same thing, except that now we're recalibrating the size of a standard deviation. Okay. So the y-intercept, again, like we said, is that the line should pass through that mean point. If it's really some kind of average line, then the regression line should go through the point x bar, y bar. Okay. And that's what we have. Okay. So we plug that into our formula and we find that a, the y-intercept, is equal to y bar minus bx bar. Okay. And again, where the slope is given by r times s sub y over s sub x. Okay. So in practice, how do you do it? Okay. And in practice, for the most part, we're going to use the calculator. Okay, so you don't have to worry about most of that stuff that the theory behind it. I wanted you to hear it. I wanted you to see it at some point, and we'll do some tutorials in class where you get a better sense of that. But for now, what's important is what you see on this page here. If you want to find the y-intercept, which is a, we're going to use the mean of the y variable, the mean of the x variable, and the slope. Okay, that'll give you the y-intercept of my regression line. If I want to find the slope of the regression line, I need to know the correlation coefficient, which is r, and I need to know the standard deviation of y, and I need to know the standard deviation of x. That will give me the slope. So these two formulas are going to be important for us in order to calculate the regression line using sort of by hand, using those things. But in practice, more often, you're going to be given the regression line, or you're going to be able to calculate it using data in your calculator. Okay, and we're going to go over that in class, so let's not worry about it right now. Okay, so thank you. That was I know a long video, and but I hope it was worth it.